Hi everyone, I'm Jack, a student from Salmon University, Malaysia. Today I would like to share a topic from mathematical analysis, which is differentiable multivariable function. Differentiability in multivariable functions is like what we learned for single variable functions, but now it's work in more dimension only. A function is differentiable at a point if it has a flat plane, or we can call a tangent plane that touch it there and make the function look most like the plane nearby. So this is important because understanding this helps us tell apart the smooth part of the function from the non-smooth ones. Multivariable differentiability is widely used in fields like physics, engineering, economics, and many more to model and optimize systems influenced by the multivariable. Then let's see what definition theorems we have there. First, let's see the definition of differentiable function. Let a domain big O be a subset of Rn that contains the point S0, and let f be a function defined on the domain O. The function f is differentiable at S0 provided that there exists a linear transformation T so that this limit is 0. So f is differentiable if it is differentiable at each point in the domain O. Okay, then see a remark here. What is this epsilon h? The differentiability of f at S0 amounts to the existence of a linear transformation T, so that fs0 plus h is equal to fx0 plus th plus the epsilon x times the length of h, where the epsilon h go to 0 as h go to 0. Yeah, the epsilon h is a very small value, then this equation is defined. Okay, let's see the theorem. Theorem 1. This theorem is for differentiable implies continuous. The first sentence is the condition we always use letter, so I just simply go through this condition. So let f be a function defined on a domain O. If the function is differentiable at x0, then it is continuous at s0. Let's see the proof. Since f is differentiable at x0, there exists a linear transformation T such that this limit go to 0. And this equal to epsilon h that we already see at the remark. From the linear algebra we learned there exists a positive number c greater than 0 such that the absolute th is less than c times the length of the h for all h in Rn. Therefore, we have this from the remark. And we apply the triangle inequality. So the th is less than c times h, the length of h. So when h go to 0, this part is 0 times c plus 0 is 0. Then obviously, length of the fx0 plus h minus fx0 is greater than or equal to 0. Thus, by squeeze theorem, this implies that the limit fx0 plus h is minus fx0 is equal to 0. So the function is continuous at s0. Okay, next, theorem 2. Let the function defined on the domain, then these three are equivalent. F is differentiable at s0 are equivalent to f has partial derivative at x0, and this limit is 0. Also equivalent to the component function fj has partial derivative at s0, and this limit equal to 0. We can see these two limits are too similar, right? Because the linear product of the gradients of component fj and h is the j row of the fx0 times the vector h. But we need a rigorous proof. Before we prove, let's see the proposition we need to use in our proof. Okay, let f be a function defined on a domain O. The function is differentiable at x0 if and only if each of its component function fj is differentiable at x0. Okay. Sorry, I don't prove this. Sorry for that, I don't prove this here. If you are interested for the proof, you can see the textbook, page 222 that I put on the reference in the end of this slide. Okay, first, we prove A implies B. Assume A is true, so we assume that function f is differentiable at x0, then there exists a t such that this limit is 0. Let M by N matrix A such that th equal to AH for I between 1 to N. This limit is 0 because this limit is true for all direction H, and obviously also true for each direction EI. After divide the H here and take AEI to the right hand side, this gives us AEI equal to limit fx0 plus h minus fx0 divide h when h goes to 0. This shows the partial xi at x0 exists and it is AEI. But we not only enough to prove partial derivative exists. If we want to prove b is true, we also need to prove the limit is equal to 0. So let's see how. Here we know AEI means the I column of matrix A, so we can write like this. Also, we know each AEI is equal to the partial xi at x0, so we can write this form. And what is this? This actually is the dfx0. So we plug A equal to dfx0 into the limit at the first we have. Then f has the partial derivative at x0 and we get this limit is 0, so b is true. Next, we prove b implies c. We assume the function has a partial derivative at x0 and this limit is 0. Then for j from 1 to m, we can write the gradient of the component function fj at x0 is the j row of the dfx0 here. So when it times a vector h means each row of dfx0 times h is the inner product of the gradient of component function and the vector h. Therefore, the component function fj has partial derivative at x0 and this limit is equal to 0. Thus, c is true. For the last part, we only need to prove c implies a is true, then these three are equivalent. Proof c implies a is very easy because we can use the proposition that I've seen before. It say, if f is differentiable at x0 if and only if each of its component functions fj is differentiable at x0. Therefore, a is equivalent to c. So we already proved these three are equivalent. Next is the last theorem we need to discuss. Let f be a function defined on a domain O. If a partial derivative f of f exists and are continuous at x0, then f is differentiable at x0. Before we prove let's see a lemma we need to use to prove this theorem. Let x0 be a point in Rn and let a function f be a function defined on an open ball center at s0 radius r. Assume that f has a first order partial derivative for each h in Rn, which the length of h is less than r that exists z1, z2 until zn in the ball such that fs0 plus h minus fs0 is equal to summation of hi times the partial xi at zi, and the length of zi might be and with the length of zi minus x naught is less than the length of h for all I between 1 and n. The proof is in the textbook, page 229. Yeah, let's see the proof. By the lemma, for each h that satisfies the length of h is between 0 and r, that exists z1, z2 until zn in the bore center at 0, x naught, and radius r, such that this ordering we have and we seen before. Then we just minus the inner product and divide the length of h on both sides. We get this. Then for all epsilon greater than 0, I from 1 to n clearly partial xi is continuous at x naught, and there exists delta I in interval 0 to r, such that if the length between zi and x naught is greater than 0 and less than delta I, then the absolute of partial xi at zi minus partial xi at x naught is less than epsilon on. Next, we take the delta is the minimum of all delta I, and it must greater than 0, obviously. If length of h is less than delta, then absolute of the partial xi, absolute of these guys is less than epsilon on. Okay, this implies that this absolute is less than or equal to the summation of the right hand side, this absolute of the right hand side. Then we know hi over the length of h must less than 1. Why? Because we can consider the two-dimension h, length of h is equal to the square root of h1 square plus h2 square, and this is greater than or equal to each h1 square or h2 square, right? Which is h1 absolute. So absolute hi over length of h must be less than 1, and this guy is less than epsilon over n. So 1 time epsilon over n is epsilon over n here. Then we get the summation, we just time the n, we get epsilon. So this means the limit is equal to 0 because less than epsilon. From theorem 2, we know a function has a partial derivative and the limit is 0 at x naught if and only if f is differentiable x and x naught. So we're done. Okay, here have a corollary which say let f be a function defined on a domain O if the partial derivative of f exists at x naught but the limit not equal to 0, then we can say f is not differentiable at x naught. Okay, the proof also in the textbook, page 227. Then let's see a simple example problem related to the differentiable multivariable function. Okay, let f be the function defined as x cubed over x squared plus y squared if the point is not 0. The function is 0 if the point is 0. Determine whether f is differentiable at 0. Okay. First, we need to find the partial x and partial y at 0, 0. Then we find the partial derivative exists and it is 1, 0. Then we let h be a vector h1, h2. Then we plug it into the limit and see what is the limit is. After do some computation, we get this. But we can't see anything here, so we need to do some case to find the limit. Before find the limit, what I want to say, if the limit is 0, then f is differentiable, right? Okay. But if the limit is not 0 or the limit does not exist, then f is not differentiable. So let the limit be v. For case 1, if the v is 0, we can choose h1 h be a sequence 1 over k 1 over k. Then the limit of f h is 0 when k go to infinity, and the limit is not equal to v. Not equal to 0, 0 is equal to v, so the limit is not equal to v. Then for case 2, if the limit v not equal to 0, we can choose the h is a sequence 0, 1 over k. Then the h is go to 0, but the limit is 0. No, that is not equal to v. For these two cases, we can conclude that the limit does not exist. So, therefore, the f is not differentiable at 0, 0. Okay, then this is the reference for this topic. Okay, so thank you very much for watching this video, and these are the reference for this topic, and this is the textbook I read, and hope you guys have a nice day. Bye bye.